Welcome to another deep dive. You know we love to get our hands dirty with the latest and greatest in tech, and today is no exception. We're diving headfirst into AI.
Yeah, AI, specifically those AI image generators and large language
The
models.
LLMs, as the cool kids are calling them these days.
Yeah.
We've got a mountain of articles, research papers, even some of those mind-bending videos to break down.
Should be fun.
Yeah, so if you're ready to pull back the curtain and see how AI really ticks,
How it actually works.
well then buckle up. Get ready for a wild ride. And hey, while you're at it, hit that like button and subscribe so you don't miss out on future deep dives.
Ooh.
You know we've got some good ones planned.
Oh, yeah.
Okay, let's start big picture here. Computers. For decades, they were basically just glorified calculators, right?
Yeah.
Crunching numbers, following instructions.
Yeah.
But AI, it's
Yeah.
different. It's like they suddenly woke up and started, thinking for themselves.
That's a great way to put it. I mean, we've definitely moved from that traditional AI, classifying data and making predictions
All right.
to this incredible new wave of what we call generative AI. And this is all about creating, brand new content, you think, like images, text, even music.
That's what just blows me away. I mean, you give
Yeah.
these AI systems a few words, like a simple prompt, and boom, they can generate like a
Mhm.
photorealistic image or write a whole captivating story.
Yeah.
It's like magic.
It does feel magical, but it's really all based on science. Fascinating science, in fact.
Okay.
These systems are built on something called neural networks. You've probably heard that term.
Oh, yeah, all the time.
Which are basically complex mathematical structures. They're inspired by, the human brain.
Okay. Neural networks. I hear that term thrown around a lot, but
Yeah.
for us non-geniuses out there, can you break it down for us? Like, what is a neural network?
So think of it like a network of interconnected nodes, kind of like a web. And each node represents a simple calculation. And those
Mhm.
calculations are all linked together in this way that allows the network to actually learn from the data that it's given.
So it's like a giant network of tiny calculators all working together.
Yeah, exactly. And these networks are trained on massive amounts of data. Think like millions of images or billions of words. And as they process all this data, they start to identify patterns and relationships.
So it's like teaching a computer to see or to read, but on a massive scale.
Yeah, that's a good analogy. And once those networks have learned those patterns, they can then use them to generate new content.
Okay, that makes sense. Let's zoom in on those AI image generators. How do they actually work? Like, I type in a cat wearing a hat, and boom, it creates a picture.
Yeah,
Seems impossible.
it's remarkable. A lot of these image generators rely on what are called diffusion models.
Diffusion models. Okay, that sounds a little intimidating. Can you break that down for us a little bit?
Okay, so imagine you start with a perfectly clear image, like pure noise, static on a TV screen. A diffusion model works by gradually adding more and more noise to that image until it becomes totally unrecognizable.
So it's like taking a beautiful painting and slowly turning it into a blurry mess.
Exactly. But here's the key. During that process of adding noise, the model is actually learning how those noise patterns relate to the original image features. It's like learning the secret code of how noise transforms an image.
Okay, so it's like learning how to scramble a message, but also how to unscramble it.
Yes, perfect. And once the model has learned that code, it can then reverse the process.
Okay.
So starting with pure noise, it can gradually remove noise, guided by the text prompt to create a brand new picture.
Oh, wow. So the text prompt is basically like telling the model which noise patterns to remove and in what order to create the desired image.
Precisely. It's like giving the model instructions on how to sculpt that noise into a masterpiece.
That's incredible. So
Yeah.
there are some really popular AI image generators out there like Delay 2 and Midjourney. What's the deal with those? What makes them special?
So they're both great examples of what diffusion models can achieve. DALL-E 2, developed by OpenAI, it's known for just incredible realism and detail. And it can even create images in different art styles or extend those existing images to create these surreal, expansive landscapes.
I've seen some of those images and they are truly mind-blowing. Like, it's hard to believe they were made by a computer.
I know. And then you have Midjourney, which is known for a more kind of artistic, dreamlike aesthetic. And it's also very accessible. It's integrated with a popular platform called Discord, so you can interact with the model and explore different creative prompts in a really engaging way.
So it's like a collaborative art studio where people are sharing ideas and experimenting with different prompts.
Yeah, that's a great way to think about it. And it really highlights the potential of these tools to democratize art and creativity.
Okay, so we've got the basics of AI image generation down. But let's shift gears and talk about large language models,
Oh.
LLMs. These are the systems behind, those chatbots that can hold conversations or write code and even compose poetry.
Exactly. LLMs are essentially AI systems that have mastered human language. They can understand the nuances of words, the grammar, and they can generate text that's often indistinguishable from something a human would write.
And the rock star of the LLM world is definitely ChatGPT, right?
ChatGPT has definitely taken the world by storm, and for good reason, I mean.
Yeah.
It's incredibly versatile. It can handle all kinds of tasks, from answering your questions to writing creative content.
Yeah, I've played around with it myself, and it's pretty amazing. It feels like you're having a conversation with an actual person, even though you know it's a machine.
That's the power of these LLMs. They've been trained on such a massive amount of text data that they've essentially learned how to communicate like humans do.
So it's like they've read every book in the library, absorbed all that knowledge.
It's a good analogy. And they use that knowledge to then generate text that is grammatically correct
Wow.
and relevant to, like, the context.
But how do they actually do that? I mean,
Yeah.
what's going on under the hood of these LLMs?
Okay. This is where things get a little more technical.
Oh boy.
But at their core, LLMs are built on what's called a transformer. It's a specific type of neural network architecture.
Okay. Another new term, transformers. What makes them so special?
Well, transformers introduce this incredibly powerful concept called an attention mechanism,
Ooh.
and it allows the model to focus on specific parts of the input text, just like a human reader would.
Okay.
This is a huge leap forward from the older language models that just process text in a linear way.
So instead of just reading words in order, they can like jump around and make connections between different parts of the text?
Exactly. They can understand the relationships between words, phrases, entire sentences.
That's incredible. So it's like they're actually comprehending the text,
Yeah.
not just like processing it.
Yeah, that's a great way to put it. And it's this ability to actually understand the context that allows LLMs to generate text that is not only grammatically correct, but also meaningful and relevant to, what's being said.
Okay. Now I'm really intrigued, but before we get too far ahead of ourselves here, before we like delve into the complexities of transformers and attention mechanisms, let's take a step back, all right, and revisit those neural networks. What's actually happening inside those webs of like interconnected nodes?
Okay. So, as we said earlier, each node in a neural network performs a simple calculation. It takes input from other nodes, multiplies those inputs by specific weights, adds them all together. We call this a weighted sum.
Okay, so we're back to those weighted sums. But how do those simple calculations allow the network to learn these complex patterns and relationships?
Well, that's where the activation functions come in. Remember, those are those special mathematical functions that introduce that nonlinearity into the network.
Right, that's the spice that allows the network to like model the complexity of the real world.
Exactly. And by combining those weighted sums and activation functions, neural networks can learn to represent incredibly complex relationships between the inputs and the outputs.
So it's like those simple ingredients combined in just the right way can create like a gourmet dish.
Mmm, delicious. And that's a great analogy. It's this complex interplay of simple calculations that gives neural networks their amazing ability to learn from data. But to really understand how that learning happens, we need to talk about training.
Okay, training. I know that's a crucial part of this whole AI process, but I'm not entirely sure what it entails. Can you shed some light on that for us?
Of course. Imagine you're teaching a child to ride a bike. You know you're providing them with instructions and support and feedback as they practice.
Right.
Well, training a neural network is kind of similar. We feed it tons of data, and we adjust its internal parameters, those weights and biases, to improve its performance on a specific task.
So it's like we're showing the network examples of what we want it to do and then like nudging it in the right direction as it learns.
That's a great way to put it. And as that network processes more and more data, it gets better and better at the task, whether that's identifying objects and images or translating languages or writing creative text.
It's amazing how effective trial and error can be when applied on such a massive scale.
It really is. And it's that ability to learn from data that sets AI apart from traditional computer programs.
Hmm.
AI systems, they're not explicitly programmed with rules. They learn those rules from the data they're exposed to.
That is mind-blowing. Okay, so before we get too carried away with the wonders of AI training, I think we need to address these multi-layer perceptrons, or MLPs, that we keep dancing around. They seem to be a crucial part of both image generation and language models.
Right.
So can we finally unveil the mystery of what they're all about?
Absolutely. MLBs are a specific type of neural network. They're commonly used as a building block in larger AI systems. They consist of multiple layers of interconnected neurons, hence the name multi-layer. And these layers are arranged in a feed-forward fashion, so information flows in one direction from the input layer to the output layer.
Okay, so we've got these layers of interconnected neurons, each one performing those weighted sums and applying those activation functions. But how does that translate into, like, storing facts or generating text?
That's where those high-dimensional spaces come in. Remember, we mentioned those earlier.
Yeah.
MLPs can be thought of as creating these complex maps of knowledge within those high-dimensional spaces. Each dimension in that space represents a different feature or concept, and the activation of a neuron tells us how much that neuron aligns with a particular direction in that space.
Okay, I'm trying to wrap my head around this. So it's like each neuron is pointing in a specific direction in this vast multidimensional space. And that direction represents a concept or a fact.
You got it. And by adjusting the weights and biases of the network during training, we can essentially move those neurons around in that space so that they align with the relationships we want the model to learn.
So it's like the model is building a mental map of knowledge where related concepts are kind of clustered together.
That's a great way to visualize it. And this map allows the model to store and retrieve information, make inferences, even generate creative output. But let's save the deeper dive into MLPs and those fascinating high-dimensional spaces for the next part of our deep dive.
All right, cliffhanger. I'm already hooked. We've covered so much ground already, from the magic of diffusion models to the power of transformers and the mystery of MLPs.
I know, it's a lot.
I can't wait to see what other secrets AI holds. We'll be back after a short break to explore those MLPs in more detail and uncover how they play a crucial role in both image generation and language models. So stay tuned.
Welcome back. Before the break, we were teasing the idea of these multi-layer perceptrons, those MLPs, and these fascinating high-dimensional spaces they create.
Yeah, those MLPs, they seem to be like the key to unlocking how AI actually stores and processes information.
They are. And to really grasp their power, let's go back to that analogy of a high-dimensional space. Imagine a map, but instead of just north, south, east, and west, there are like countless directions, each one representing a different feature or concept.
So it's like a map with infinite dimensions, where every direction could be, like color, shape, texture, or even like more abstract ideas.
Exactly. And each neuron in the MLP can be thought of as like a point in that space. And its location is determined by its activations, which are influenced by those weighted sums and activation functions that we discussed earlier.
So the stronger a neuron's activation, the more it aligns with the specific direction in that space. And that direction, in turn, represents a particular concept.
Exactly. And during training, the model learns to adjust the weights and biases of those neurons. It's essentially moving them around in this high-dimensional space to create clusters of related concepts.
So it's like the model is organizing its knowledge, placing similar things closer together in this mental map.
That's a great way to think about it. For example, imagine a neuron that represents the concept of cat. During training, whenever the model encounters images or text related to cats, that neuron gets activated.
So it's like that neuron lights up whenever the model is thinking about cats.
Exactly. And as the model learns more and more about cats, it adjusts the connections between that neuron and other neurons that represent like related concepts like furry, four-legged, or meows.
So it's building a web of associations where the concept of cat is linked to all these other related concepts in its mental map.
Exactly. And this web of associations allows the model to make inferences and even generate creative outputs. Like if the model sees an image of a fluffy, four-legged creature that meows, it can activate that cat neuron, even if it's never seen that specific image before.
It's like the model is using its knowledge of cats to recognize new instances of cats that it's never encountered before.
That's the power of these high-dimensional spaces and those intricate webs of associations. They allow the model to generalize its knowledge and apply it to new situations.
This is just incredible. So these MLPs are essentially creating these detailed maps of knowledge within these high-dimensional spaces. But how does that knowledge actually get used in tasks like image generation or language modeling?
Well, that's a great question. Let's take image generation as an example. Remember those diffusion models we talked about? They start with just pure noise and gradually remove it to create an image.
Right, and the text prompt guides the model on which noise patterns to remove.
Exactly. But where does that guidance actually come from? That's where the MLPs come in. That text prompt is first processed by an MLP, which basically translates it into a set of activations within that high-dimensional space.
So it's like the MLP is converting those words into a specific location on that knowledge map.
That's a great way to think about it. And that location then serves as like a guide for that diffusion model, telling it which features and concepts to emphasize as it removes noise from the image.
So it's like the MLP is providing a blueprint for the image
Yep.
based on the text prompt.
Precisely. It's telling the diffusion model, okay, we want an image of a cat wearing a hat, so focus on those features as you sculpt the noise.
That makes so much sense. So the MLPs are essentially bridging the gap between language and visual representation. It's allowing that text prompt to guide the image generation process.
Exactly. And the same principle applies to language models. The MLPs help to translate that input text into a meaningful representation within that high-dimensional space.
So it's like the MLP is understanding the meaning of the text and then using that understanding to guide the generation of new text.
Exactly. It's like the MLP is saying, okay, I get it. You're asking me to write a poem about a cat, so let me access all my knowledge of cats, poetry, and language to create something that fits those criteria.
It's just really mind-blowing. It's like we're like peering into the inner workings of the AI's mind and seeing how it organizes and manipulates knowledge to achieve these incredible feats.
It is a really exciting time to be exploring AI, and as we develop larger and more sophisticated models, those maps of knowledge are only going to become more detailed and intricate.
It's amazing to think what these models might be capable of in the future. But for now, let's shift our focus back to those transformers and those attention mechanisms you mentioned earlier. I'm really eager to understand how those work and how they contribute to the power of LLMs.
All right, let's dive into that. Remember, transformers are a specific type of neural network architecture that's really revolutionized language processing.
Right. And they're powered by those attention mechanisms which allow the model to focus on specific parts of the input
Oh,
text.
exactly. But before we get into the mechanics of attention, it's helpful to understand why it's such a big deal. Traditional language models, they process text in a linear fashion, like reading one word after another.
So they didn't really understand the relationships between words or like the overall context of the sentence.
That's right. But humans don't read that way. We jump around making connections between different parts of the text to extract meaning.
Yeah, we focus on like the key words and phrases that convey the most important information.
Exactly. And that's what attention mechanisms allow LLMs to do. They allow the model to focus on the most relevant parts of the input text, just like a human reader would.
So instead of just processing words in order, they can identify the key words and phrases that carry the most meaning.
Exactly. And they use this contextual information to generate more accurate and relevant outputs. But let's break down how this actually works.
Okay, I'm ready for that technical deep dive. Walk us through how an attention mechanism actually operates.
All right. Imagine you feed a sentence into a transformer. Okay, the first step is to convert each word into a vector. This represents its meaning. We covered this before. It's like giving each word, a unique numerical code.
Right, those embeddings that capture the essence of each word.
Now, the attention mechanism comes into play. What it does is it calculates a score for every single pair of words in the sentence, and this score represents how much attention one word should pay to another.
So it's like each word is evaluating its relationship to every other word in the sentence.
That's a good way to put it. And these scores, they're calculated based on the similarity between the word vectors and their positions in the sentence.
Okay, so words that are semantically related and close together in the sentence, they're going to get higher attention scores.
Exactly. And those scores are then used to create a weighted sum of the word vectors. And this weighted sum essentially amplifies the importance of the words that are deemed most relevant to the current context.
So it's like shining a spotlight on the key words and phrases while dimming the lights on the less important ones.
That's a great analogy. And this weighted sum, which now contains that contextual information, is then passed on to the next layer of the transformer.
So the model is not just processing individual words anymore. It's processing words in relation to each other, taking into account their meaning and their context.
Precisely. And this process is repeated multiple times within the transformer, with each layer building on the insights of the previous layer.
So it's like the model is refining its understanding of the text with each layer, extracting more and more nuanced meaning.
That's a great way to put it. And this multi-layered attention mechanism is what gives transformers their incredible ability to process and understand language so effectively.
Okay, I'm starting to see how this attention mechanism is such a game changer for language models. But earlier you mentioned something called multi-headed attention. What's that all about? Is it like having multiple attention mechanisms working in parallel?
You got it. Multi-headed attention is a way to enhance that attention mechanism even more by running it multiple times simultaneously, each time with a different focus.
So instead of just one set of attention scores, we get multiple sets, each highlighting different aspects of the text.
Exactly. For example, one attention head might focus on the grammatical relationships between words, while another head might focus on the semantic relationships, and yet another head might focus on, like, the overall sentiment of the sentence.
So it's like having a team of experts, each analyzing the text from a different perspective.
That's a great analogy. And this multifaceted analysis allows the model to capture a much richer and more nuanced understanding of the text.
I'm really starting to see how this all fits together. We have those MLPs creating those intricate maps of knowledge, and then those transformers with their attention mechanisms are using that knowledge to understand and generate language in a way that's so similar to how we do it.
It really is a testament to the ingenuity of AI researchers and the power of these models. But we've really only scratched the surface of what these transformers can do. There's still so much more to explore, like those encoder and decoder layers that work together to process and generate text. And then there's this fascinating concept of emergent capabilities, where these models start doing things that we never explicitly programmed them to do.
Okay, now I'm really intrigued. We've covered so much ground already, from those diffusion models to MLPs and these amazing attention mechanisms. But I can't wait to delve into those encoder and decoder layers and uncover those emergent capabilities that you mentioned. I have a feeling there's a whole lot more AI magic waiting to be discovered.
You're absolutely right. The world of AI is full of surprises and possibilities. And we'll be back after a short break to explore those next chapters in our AI journey. So stay tuned.
Welcome back to the Deep Dive. We're wrapping up our epic journey into the heart of AI, and I'm still reeling from all the mind-blowing concepts we've uncovered.
It's been quite a ride, hasn't it? From those amazing diffusion models that can create images from pure noise,
Right.
to those intricate MLPs, those multi-layer perceptrons that build these maps of knowledge in high-dimensional space.
Yeah.
And those powerful transformers, with their attention mechanisms that allow AI to understand context like never before.
Right. And now I'm really curious about those encoder and decoder layers you mentioned.
Yeah.
Those sound like they're key players in this whole language processing game.
They are. Think of the encoder as the part of the transformer that reads and understands the input text, like a superpowered speed reader. It can absorb vast amounts of information and distill it into a concentrated form.
So it's taking those words and sentences and turning them into some kind of like compressed code that captures their meaning?
That's a good way to put it, yeah. And then the decoder comes in. It takes that compressed code from the encoder and it uses it to generate the output text.
So it's like the decoder is translating that, like secret code, back into human-readable language.
Exactly. And it does this by carefully considering the context and the meaning that was encoded by the encoder, making sure that the output is both grammatically correct and relevant to the input.
Okay, so we have this dynamic duo,
Hmm.
the encoder and decoder. They're working together to process and generate language.
Yeah.
But how do they actually communicate with each other? It's not like they're passing, like, notes back and forth, right?
Exactly, no. They communicate through what's called cross-attention. Remember those attention scores we talked about earlier?
Yeah,
Those were all about words within the same sentence paying attention to each other.
right. That was self-attention, where
Yeah.
each word is kind of evaluating its relationship to all the other words in the sentence.
Exactly. But with cross-attention, the decoder can actually look back at the entire input text, using those attention scores to identify the most relevant parts of the input for generating the output.
So it's like the decoder's having a conversation with the encoder saying, hey, remind me what was important about that input text so I can generate the best possible output.
That's a great way to visualize it. And this cross-attention mechanism is incredibly powerful because it allows the decoder to generate output that is really tightly coupled to the meaning and context of the input.
It's like the encoder is providing like a roadmap for the decoder, guiding it towards the most meaningful and relevant output.
Exactly. And this really intricate dance between the encoder and the decoder is what allows these transformers to perform this wide range of language tasks, from translation to summarization to even creative writing. But there's another really fascinating aspect of these large language models that we haven't really touched on yet, and that's emergent capabilities.
Oh, yes. You mentioned this earlier, and I've been dying to learn more about it. This idea that as these models get larger and are trained on more and more data, they start doing things that even their creators didn't expect.
That's right. It's one of the most intriguing and maybe even a little unsettling aspects of modern AI. As we push the boundaries of model size and training data, we start to see these abilities emerge that we never explicitly programmed or taught the models. Can you give us some examples of these emerging capabilities? Like what kind of unexpected things are these models doing?
So one really striking example is the ability of these large language models to perform tasks that require, like, reasoning or problem solving. For instance, a model might be able to solve a logic puzzle or generate a coherent story, like with a complex plot, even though it was never specifically trained on those tasks.
So it's like these abilities are emerging organically from the sheer scale of the model's knowledge and its ability to process information.
Exactly. It's as if the model is starting to exhibit a form of what we might call generalized intelligence, allowing it to apply its knowledge to new and unexpected situations. It's a testament to the power of these models to learn and adapt beyond the specific tasks they were trained for.
Wow. That's both exciting and a little bit mind-boggling. It really makes you wonder what other capabilities might emerge as these models continue to grow and evolve.
It does, and it raises some important questions about the future of AI and its potential impact on society. But one thing's for sure, this is just the beginning of a new era of computing, and we're only just scratching the surface of what AI can achieve.
Well, I think my brain is officially full after this deep dive. We've gone from those mind-bending diffusion models to those intricate maps of knowledge to those powerful encoder-decoder duos. It's clear that AI is rapidly evolving, and understanding these technologies is more important than ever.
I completely agree. And as always, we encourage you to keep exploring and keep learning and keep asking questions. The world of AI is full of wonder and possibilities.
And on that note, we'll have to wrap up this deep dive. But before we go, we want to remind everyone to hit that like button and subscribe to catch all our future episodes where we'll continue to explore the fascinating world of technology and innovation.
Until then, stay curious, keep those brains engaged, and we'll see you next time on The Deep Dive.